Hey everyone, my name's Feet. I am here to talk about serving models, large language models in particular. I work for Red Hat. I work as an AI community architect, which means we work with open source projects to build their communities, to support them in really any way possible. Ultimately, we try to help open source live forever. And so that's where we live in these ways of getting projects out, donated into foundations, support the foundations and things like that. So real quick, show of hands, anyone here serve a model ever locally on a machine, on data center hardware, just playing around with OpenClaw maybe? Okay, a few people, that's good. So we're gonna talk about how you can serve models on Kubernetes with a project called llm-d. So before I dive into that though, we need to talk about VLLM. So who here has heard of VLLM? Anyone? Awesome. So the goal of VLLM is to build the fastest and easiest to use open source LLM inference and serving engine. It's got wide support for a variety of GPUs, data center GPUs, consumer hardware, even the unified memory in your MacBooks, you can use VLLM on. And so if the goal of VLLM is to make the serving process as efficient as possible, we can make the hardware resources required to serve these models as small as possible, and ultimately try to make doing this all as easy as possible. So VLLM is at this point the most popular LLM serving engine, over 80,000 stars, for whatever that means, seeing about 2,000 PRs a month. And there's thousands of contributors that are working on this across a whole variety of companies. It's supporting, I think, over about 100 models at this point, and they actually work extremely closely with model providers to make sure that they can have day one support for a lot of models as they come out. It is part of the PyTorch Foundation. So why do we even need something like VLLM? Like, why do we need a specialized software for serving a large language model? And maybe this is kind of a simplistic answer, but production inference serving of LLMs is a really hard problem because we're dealing with batch sizes greater than one. It means we have multiple concurrent users in a system. So VLLM's real job is to manage those requests. And we'll talk through why that's a hard problem shortly. So VLLM's job, efficiently schedule the requests, manage the internal state of those requests, and make GPUs go burr. So let's talk a little bit about how LLMs work in the first place. So if you think of a model like Llama, it's a function that computes the probability distribution of the next token based on a sequence of tokens. So this equation is representing this idea here. If you remember multivariable calculus, you're at home. So if you don't, it's fine. I was told there'd be no math. So when we turn to inference, it's not one single forward pass through a model to generate a text. LLM systems generate roughly one word at a time in a sequence or a token. So the image on the right is what we're doing here. For a prompt of 3 tokens, the quick brown, the next token being fox for a sequence of 4 tokens. We pass the model to generate the 5th token, the quick brown fox jumped. So the idea here is that LLM inference is really hard and compute intensive because one request to generate those 1,000 tokens requires 1,000 passes through that, let's say, trillion parameter model. And there's a lot of latency associated with that, which I'm sure you all know. Think about the average request to a chatbot. It can take like 30 seconds, a minute, even more, some of the thinking models that are out there. And so we need a way to interleave these requests and make progress on them at the same time. So kind of an old way it was handled was dynamic batching, where you'd kind of batch these requests together, wait for them all to finish, and then you could complete it. But VLLM brought in a concept of continuous batching. So instead of waiting for that whole batch to finish, the engine's evaluating the batch after every token, and when one finishes, it evicts that from the batch. A waiting request comes in and takes its place. So again, what's the goal? The GPUs need to be maxed out like at all possible. It's kind of funny because like I'm an old sysadmin, kind of like I hate all technology type sysadmin. And in the old days, it's like you would have an alarm that was like, oh no, my CPU is 10%. That's too high. They must be idle at all times. And now we've flipped it on its head where it's like, no, if those GPUs are not smoking with fire coming out of them, we are wasting money. So how do you make them as efficient as possible? And that's where it comes in. So this idea that there's these multiple passes through a model implies that there's some sort of internal state that has to be managed during that LLM generation process. So this contrasts with a predictive model where there's no internal state. You get a request, you pass it through the model, and you get an outputted result. So what's the most obvious optimization here if we have this state is how do we avoid recomputing those tokens through every forward pass of that for every new word? So we want to shift from a function that reevaluates that entire sequence history from scratch to a function where we can just reuse that internal state. And so this is what's known as attention, which is something you might have heard before. And a state we're talking about is something called the KV-cache. And it's a terrible name for it because it's not KV and it's not really a cache. You aren't storing lightweight strings in Redis. You're dealing with massive multi-gigabyte matrix tensors trapped in GPU memory. So completely different beast. And if you're like, what the hell is a tensor? I aim to like demystify words in AI because we make up words and they sound really fancy. And a tensor, like a 2D tensor, you're like, whoa, that is a crazy mathematical concept. It's like, it's a spreadsheet, 2D tensor. Like it's a table, right, of numbers. But of course it does actually get complex because then you have 3D tensors, which are like a cube of spreadsheets. And then it can go multi-dimensional as well. And you just have cubes of cubes of cubes and you can't even visualize them anymore. But the key thing that I'm trying to explain is that these are huge numbers, large amounts of data. So if we look at model architecture, that attention layer is actually the only layer in the network that has to look back at prior tokens. So because of that, we could capture those K and V vectors and we can compute the next token without having to recompute them all over again. So again, you shift from having to recompute your prompt tokens over and over. You only have to compute the math for that one single token during the decode phase. We're going to talk a lot more about that. And we can reuse that cache state for the rest. So this is a massive optimization. But KV caching makes that whole system a lot more complex. So why is it complex? Because the KV cache is huge. So to give you some context, if you look at a model like Llama 2 running on an A100 40 gig, KV cache swallows up almost half of the system memory. And this is GPU memory too. So this isn't even like RAM. RAM is like cheap memory, not in this economy, but this is GPU memory. So for a request hitting something like a Llama 3, every 10,000 tokens is about 1 gigabyte of RAM. So if you scale that up to production on a modern H100, B200 servers, dealing with long context windows, hundreds of active requests simultaneously, you can see how it adds up massive multi-gigabyte footprints of memory. And this has to be managed on the fly. Like we're actively communicating with the KV cache. So while this KV caching optimization is really critical for performance, it's a huge engineering challenge. How do we actually allocate and manage all this memory in a really granular and efficient way? So this is a kind of a breakthrough with VLLM. It's a technique called page detention. And so for those of you in the room with operating systems background, this is actually going to sound really familiar. The core idea is let's manage that KV cache memory the same way as a traditional OS manages virtual memory. And so how that works is instead of forcing the GPU just to allocate giant contiguous chunks of physical memory in a request, we'll split it up. And so then from the model perspective, each request has a clean, logical view of the KV cache. But behind the scenes, those KV cache blocks, they're scattered randomly across the physical memory, and they just fill in wherever is open. But this was really the spark that kicked off the entire VLLM community a few years ago. Combining things like continuous batching, virtual memory concepts, you now have this really fine-grained cache management. And this is the fundamental blueprint for almost how all LLM servers operate today. Even proprietary engines have adopted this kind of paged architecture. So a great phase to keep in mind here is a couple of these terms. Prefill is expensive, decode is cheap, and then caching is kind of what bridges it together. So as a request hits your server, step one is prefill. The model processes that entire input prompt all at once, and it computes attention over every single token pair. So attention scales quadratically, meaning double the in-prompt length, 4 times the work, 10 times the prompt, 10 times the work, it gets harder and harder. This is matrix multiplication, so extremely compute heavy. While doing all that heavy lifting, the model is saving its working memory into that KV cache. Now, when that's done, we move to the next step, which is decode. So this is relatively easy, as we're just generating 1 token at a time. And this operates linearly. So if you're generating twice as many tokens, it's twice as much work. It's no surprises, hopefully no explosions. The model does not have to recompute the pass because it's reading and extending that KV cache. The cache is really the only reason that step 2 doesn't crush our system performance in the first place. So we know we can cache this data, and because of that, we can start doing some really clever optimizations for things like shared prefixes. And so systems like vLLM leverage something called prefix-caching. So if 2 requests share the same token prefix, like what is the capital of America? And another request comes in, what is the capital of France? It can skip the entire prefill phase entirely for that shared portion, right? We've already computed, we've already done the work. It's already there. Let's not do it again. And those are simple examples, but like, what about a massive system prompt? That could be 2,000 tokens, 5,000 tokens, like they get bigger and bigger. So again, real benchmarks showing 7x improvement, no extra compute required for prefix caching. And again, huge optimization, and it works beautifully on a single GPU instance. But the second you actually scale this out and add a second pod to your cluster, this is where the strategy really breaks down. So why does it break down? Well, your load balancer is cache blind, right? We've created this new cache, the KV cache, but the load balancer doesn't know anything about it. So if you were to put this in some sort of real production environment, of course, you're not running a single GPU, you're going to have a multi-pod deployment. If you use a standard load balancer, imagining it's routing traffic like metrics on round robin or least connections or CPU utilization, it has no idea what tokens are actually in the request. And so it destroys the cache locality. Your cache is living on every vLLM server in your pod, and a massive fleet of these is going to round robin across. That's the default behavior, but it's going to kill your performance. So this is where llm-d comes into play. It turns out that just like inside a single inference server, we can take advantage of that transformer architecture to make things more efficient. We can actually apply the same thinking at a cluster scale as well. So llm-d actually started by taking vLLM plus Kubernetes, operationalize inference, make it really flexible, make it cross-platform. We implement these optimizations directly inside of Kubernetes. So it allows people who are familiar with Kubernetes to have this single API that they already know and love. And it allows the entire cluster to really exploit the fundamentals KV caching subsystem to get those same performance advantages across a large number of machines. But because production environments are rarely uniform, it's actually designed from the ground up to be cross-platform. So right now we're supporting accelerators from AMD, NVIDIA, Google TPUs, and more. And Intel, I think XPU support's coming soon. And I've been more focused on vLLM, but llm-d is also designed to support different model servers as well, SGLang being one of them. So again, it's trying to be this singular API for model serving on Kubernetes. So this project was founded last year. Teams from CoreWeave and Google and IBM Research, NVIDIA, AMD, and many more. And this project actually just joined the CNCF a few months ago as a sandbox project. So that was a really great goal. So we're trying to stop treating infrastructure and model architecture as two separate problems. By integrating them, we can enable this like true cluster scale optimization inside of that standard Kubernetes operational framework. So at this point, it should be clear, like, why do we need this? LLM requests are totally different than standard HTTP requests that we've been scaling for decades. Standard web traffic microservices, they're fast, they're uniform, they're cheap. The QPS are orders of magnitude higher than an LLM would be. So standard practice on Kubernetes, you create a deployment, scale out the replicas, put a microservice load balancer in front, and just do some round robin load balancing or random load balancing. Everyone's happy, right? Maybe not the databases. Let's not worry about scaling databases. That's a separate thing. But for LLMs, we can do a lot better than that. LLM requests, again, they look nothing like traditional web traffic. They're slow, they're completely non-uniform, and they're really, really, really expensive. You could have a request that is a very tiny prompt, but it runs a massive long generation phase, right? These are hard to optimize. Or you have these highly repeated patterns happening in agentic workflows and multi-turn chat. So this gives us an opportunity to exploit the system. We can leverage and share that KV cache we talked about before across the cluster instead of letting the blind load balancer destroy the cache locality. Second, because we have those distinct prefill and decode phases we talked about, we can actually specialize the servers for each specific workload. So again, that's the overall idea with llm-d. So this is actually the architecture of llm-d. And this is a pretty fast moving project. I think 0.7 just shipped. I just grabbed this from the docs, so it should be up to date. But the earlier one I had from like a month ago was a little different. So, but basically how this works is you have a request, it hits the llm-d router layer. The proxy doesn't just guess where to send it. It actually passes it, the context over to the llm-d EPP, and that's our endpoint picker. So the EPP is a library of scrapers, filters, scorers, and it probes the model replicas that are all down in that inference pool. It knows real-time load and the exact KV-cache state, and whether a node is running prefill or decode, and it can score basically the best pod for that request. So when it scores it, it passes the decision back, and the proxy then routes the traffic down to the selected pod. So again, instead of some naive load balancer just throwing traffic at random, the entire Kubernetes cluster from EPP down to the autoscaler, we have the variant autoscaler there, is aware of the LLM's internal state. So serving models is hard, and it's really complex. And distributed systems, turns out, are really hard and complex. So the concept of llm-d is having these well-lit paths. And the idea is it should be able to walk you through from a starting point of basically nothing, working towards a solution that you can adjust based on your use case. Because again, are you serving agentic workloads? Are you serving user like multi-turn chats, document summaries? I mean, it goes on and on and on, the different workloads, and they all will look different in your deployments. So the other goal of these is that they should be rigorously tested and benchmarked across a variety of infrastructure. I think one of the coolest parts of AI inference projects is how much we're back to benchmarking performance and holding our systems to these standards. But it makes sense, right? You spend millions of dollars potentially on hardware. How do you actually know you're getting all the performance out of it? You could have a small configuration change and maybe only getting 50% performance, costing real money. So because of these benchmarks, you'll know for X model on Y hardware and these specific settings, you should see about this performance. So the first path, and we'll talk about each one of these. The first one's an optimized baseline. This leverages that prefix-aware and load-aware routing that we were just talking about. The second one, wide expert parallelism. This is also known as wide EP. This is for scaling out really large mixture of expert models. Think like a DeepSeek model was like the first like MOE model. Advanced KV-cache management intelligently handles that attention state we talked about before. And then also we have this prefill decode disaggregation. And this physically separates compute and memory workloads across these different GPU pools. And we'll talk more about why that's important. So again, we know those repeated prompts are really common in production. You fire up cursor and you're hammering away at some vibe coding thing. You're adding on to the prompt every single time without any sort of ability to route based on the prefix, all those tokens prior. It's got to recompute all that all over again, incredibly slow. So we solve this with a prefix-cache-aware routing. So the EPP, remember that's the scorer, can maintain a real-time view of the KV-cache state inside of each individual pod. We can track this in a few different ways. We have one that's called the approximate version, where the EPP is basically has an estimated prefix cache tree, and it keeps that one internal. And we can also pair that with a load-aware routing. Instead of just having load-aware by itself, if you do load-aware plus prefix caching, you'll send it to a node that has the tokens that have already been stored in the cache. But with load-aware, you can make sure you don't send it to a node that's already overloaded with something else. Because it could take longer to wait for that node to be ready, even though it has the tokens already calculated, then just recalculating them all over again. There's also a precise version. And this one's kind of interesting because the VLM pods themselves will stream real-time events up to the EPP. So then that gives the EPP this kind of globally consistent state of the cluster's cache. And so this is what happens to your actual performance benchmarks when you switch this on. So again, no-brainer if you're running any sort of repeated workloads. So here we're benchmarking total throughput and mean TTFT, that's time to first token, against the incoming queries per second. So the green and red lines are the top graph and the bottom. That's standard random scheduling load-aware routing. And you can see they hit a wall really fast, right? Makes sense because the GPUs are just recalculating all those tokens again. There's just only so fast we can go. But that blue line up above, that's actually tracking our precise scheduling path. So in this workload benchmark, this is 16 H100s. Obviously, difference is night and day. It's a 57x faster response time on TTFT. So I'm only going to touch on this one in like one slide. This is YDP. There, you could watch a whole conference talk just about this topic. It's pretty in depth. But the idea here is specifically, how do you scale out a massive mixture of expert model, like again, an architecture like a DeepSeek. So when a model does get that big, it's just impossible to cram it all on a single machine. So what do? You have to slice the different expert layers horizontally across your fleet of nodes. So what llm-d does here is try to handle all of that multi-node orchestration, but natively inside of Kubernetes, and it uses automation tools like leader worker set to make that happen. And again, back to our EPP, that's really the magic. It's now aware of this layout and how to map the traffic across that whole kind of matrix of GPUs behind the scenes. So the KV cache management well-lit path, this is basically a way in which the system can help you manage that KV cache. So kind of one side of KV cache management is how do we offload that cache in a vertical way, like think a GPU fills up and llm-d can drop those cache blocks into like a cheaper local RAM, CPU RAM versus GPU RAM. And again, the EPP has the global index of the memory. So if the prompt hits Envoy again, then it can just pull the cache right back up. The other side would be something like a horizontal offload. So instead of keeping the cache trapped on just one machine, let's stream it out to a global shared storage, and think of like long-running user histories, right? In a chat system, you might want to come back to it days, weeks, months later. You don't actually want to you've already done the work, right? You've already calculated those tokens. Just pull it back from a shared storage. And the project has a pretty wide and growing support, different cache engines like LM-cache, Mooncake. I've even seen some recent work to offload to a Ceph object store. So a lot of different ways to essentially like get this work off of these GPUs if you're gonna use them again later. So again, this allows you to turn your standard data center memory and storage into this elastic extension of your GPUs. It's probably the reason why like hard drives and consumer RAM has gone up in price. If you're really wondering like, wow, how does that have anything to do with AI? It's probably because we're offloading all of this data to it. So I think this last well path I'm going to talk about, this is a really elegant way we can leverage the KV cache subsystem with this concept of PD disaggregation. So disaggregating prefill and decode. So we talked about how they're these different architectural workloads. Prefill being compute heavy, and decode is a memory bound process. So the core idea here is if we specialize these VLLM servers so that only some of them handle prefill and have others handle only decode, then we can have a distributed system that is much more efficient. And the only way that's going to actually work is if we pass the state between them. So that's where this KV cache transferring comes in. So what we can do is you could run prefill on one machine, you can grab the cache, you can send it to a decode instance, and then the decoder can generate text without anyone ever having to look at the input prompt. So like, why would you do this in the first place? So walking through this architecture guide, how this works is Envoy requests its Envoy, and the EPP actually sends it to a decode pod. And there's a sidecar that runs there that helps coordinate this process. And then from there, it sends the request to a prefill pod. And so again, the prefill is the thing that's calculating the attention pair of the initial input prompt. It sends over, when it's done, a KV transfer request and says, hey, here's physically where those blocks I've computed exist. Here's where you can get them. And the decode pod can capture those. So again, these caches are massive, gigabytes, hundreds of gigabytes, tens, hundreds of gigabytes. So we're using data center class networking to send this stuff over. We're using technologies like Nixel, which is a technology from NVIDIA. AMD also has similar technologies for their hardware. And what that does is like copy the blocks physically from GPU to GPU in an asynchronous way. And so when that's done, the decode pod now has all of the input tokens calculated, and it can just stream them out to the user. So there's a massive incoming prompt. If by scaling it out this way, if an incoming prompt comes in, it will never interfere with ongoing token generation on the decode side. So it's pretty complicated to do this. Is it really worth the complexity? And it really comes down to what we spoke about prior is we're basically splitting the GPUs to focus on two different natures of computation because they are different. So let's optimize them differently. And this graph here just kind of shows the performance differences between decoding and prefill. So when it comes to scaling and running lots of prefill and decode nodes, what this graph is actually showing is that decode is just scaling better than prefill does with what's called a higher tensor parallel size, right? Splitting the model across GPUs. So on the prefill side, your output tokens take a greater hit when you increase the concurrency, but on decode, this happens less. So what this suggests is we want to have more concurrency basically on our decoders versus prefillers. So the prefillers here, they're short-lived, right? Prompt comes in and they crunch through it in a few iterations, then they move on. But decode actually has to sit there with all of that KV cache generating text one token at a time, and it's holding onto the cache the whole time. So what these graphs show here is actually telemetry from a YDP deployment on a GB200 cluster. So the top chart on the right is prefill KV cache utilization. It's practically 0% because those prompts are happening very fast and they don't leave a footprint. But at the bottom chart, the decode KV cache, it's about spiking up to 65. And again, it's grinding through all of these concurrent generation loops. So if you force a single GPU to handle both workloads, your memory is going to get choked. By disaggregating them out, we can then size the hardware pools perfectly based on our workload. And so on the left side of the chart, KV cache aware routing, that's our blue bars, blows away standard load balancing, which we kind of talked about before. So if we kind of put this all together, when we compare these different configurations of prefill and decode, what we see on the chart is that disaggregated serving kind of wins right in the middle. The reason is that LLM inference is this trade-off between interactivity, how fast the user gets tokens, and efficiency, which is like GPU throughput and cluster cost. So if you want high efficiency, you want the smallest aggregated deployment possible. And that would be a single GPU instance. So you could pack everyone onto one node. Your CFO would probably love it, but your individual user speeds would be pretty terrible because as we learned, as concurrency scales up, your speeds fall off a cliff. So let's flip it out and say, if you want high interactivity, like blazing fast user speeds, you really need a massive deployment. But as we saw a few slides ago, the GPU efficiency is going to completely tank because the GPUs will spend too much time talking to each other when you scale up that concurrency on prefill. But if you're in the middle, and this is where a lot of production workloads actually live, you can break away that trade-off. So to optimize for your SLO, use a lot of small unsplit prefillers at a lower cost, and then feed all of those caches into a large decoder, and it ramps up your concurrency. So kind of getting the best of both worlds. And so again, this is a massive win for PD disaggregation, is that it's taking prefill off your critical path for decodes. So like standard setup, your single GPU, your GPU pauses code, like I say code generation because we use it for coding, but the token generation pauses when a new input prompt comes in. So if you're waiting for a response, that stream is going to stop when the prefill is happening. And so that's what this P99 intertoken latency here, that red line, lags all the way up to 880 milliseconds because of that constant interruption. But because with llm-d, we isolate the decoders, we put them in their own pool, they don't get blocked by incoming requests. They just stream smoothly along that blue line, just 110 milliseconds, 8x drop in tail latency because we're separating those technologies. So, but again, the real power of this framework is not just picking one strategy. It's actually composing them all together in llm-d simultaneously. So you could say, take a wide EP plus PD disaggregation and intelligently routing, KV cache routing, put it all together. So in this benchmark we've got 4 separate worker pools dedicated just to handling prompts. That's our prefill pods. And then the individual pool is split across 8 highly connected GPUs. We feed all of those prefills into a massive unified generation pool. That's 32 GPUs just for the decode side. And it's holding all of the active model experts to stream those tokens out. So in this scenario, we run a brutal multi-turn agentic loop. It's inputting of 10,000 tokens, output sequence link of 2,000 tokens, and continually adding over this 5-turn conversation. And essentially, like without prefix caching, your prefillers are never going to keep up and your decoders are sitting idle. And this is how, again, we want these GPUs to be running at 100% all the time. So these graphs are a little backwards. Usually you put like the before and then the after, and it's the after and then the before. But on that side of the graph, you know, the prefill cache hit rate is basically 0, right? If we don't have KV-aware routing turned on, we're calculating over and over and over again. And again, prefill waiting requests on the right side, or your right, my left, are very, very high. A lot of requests are waiting, again, because we're doing all this recalculation. But by more smartly routing based on where the KV cache is and the prefix caching, instead we get incredibly high prefix cache hit rates, and our waiting requests drop to very, very low, nearly 0. And this is really the power of having this cache that is flexible and being able to distribute it across systems. So that was a lot of stuff in a really short amount of time. And this is like the tip of the iceberg of this project. There's a lot of things that are working inside here. There's a lot of different teams on this. Definitely recommend checking out the website. You can follow some QR codes here. We just recently shipped a huge docs release. A lot of people got involved in that, expanding out the documents and the guides that you can use to get started. You can join our community Slack if you want to dive into any of these topics. There's all the experts that are living in there. And there's a lot of ways to get involved. You don't have to be an expert in model serving or, you know, math and all these very difficult concepts that, you know, probably haven't done since college. You know, we're deploying a massive, complex distributed system to Kubernetes, which is what a lot of us have been doing in our careers for a long time. So you can get involved in how does installation work? We're using Helm charts and customize. What about monitoring and tracing and telemetry? How do you trace the performance of your system? This, again, massive distributed system. We're doing interesting work with Grafana and Prometheus for that. So anyway, that's all I have for you today. Again, find more by scanning the QR codes, and you can find me on basically LinkedIn is probably the only place I exist online right now. So anyway, thank you all so much.